Hello, everybody. Okay, we are going to go through our notes on gears, pulley drives, and sprockets, and just kind of touch upon it quickly. This is something where you do want to practice the math as we go along to double check that you're understanding it and being able to calculate everything. All right, so first things first, let's move along with our slide here. The idea with gears, pulleys, and sprockets, it's just that something will be driven on one object, something that's going to be spinning, okay, and somehow, depending if it's a gear, a pulley system, or a sprocket, will cause something else to spin. All right, and the reason we use it is for a bunch of reasons. Right there, changing the speed of an object as it rotates, changing the direction of it, and changing torque to increase torque. Okay. If you ever look at a car, looking at the front part of a car, open up the hood and you look at the pulley system, there will be a drivetrain, or not the drivetrain, but a pulley system inside of for all your belts. Okay. So you'll have a belt and it's going to be connected to all different types of motors. And it's extremely important. Okay. And that's one of these examples where they'll have different sizes. They'll have different, and that'll cause things to spin faster or slower, which means also it could be giving more torque or less torque. So it's an extremely important and helpful thing in your car and in all other places. And you see the examples there. So we have three examples. We have the far left, that is a gear train. Okay. Gears will be circles with teeth that connect directly to another circle with teeth in it. All right, the next one is going to be the pulley system. All right, and the pulley system has a belt without any teeth and is just going to cause something to spin. So that's the bottom of a lawnmower, of a rotting lawnmower. The third one is a sprocket, and a sprocket, I always like saying sprocket, but a sprocket is going to be a chain with teeth. And it looks like, if you looked at what it's connected to, they almost look like gears, but they're going to be the circles with the teeth are designed to collect that chain. They're not designed to connect with another gear. All right, so there we go. Let's do a quick rundown. Let's talk about gears. All right, a gear train is going to be anything causing it, an object to spin. Okay, it's going to have torque to it. Torque, again, is the force. It's similar to the word force. Force causes something to go in a straight line, while torque causes something to rotate. All right. So you see there, gear train always made with two or more gears. It causes motion. That's great. And it's always driven from the driver gear to the driven gear. Okay. The driver for all of these will be the main object that causes all the other objects to spin. Okay. Now, looking here, we have gears. When gears are stuck together, we call them mated. All right. So mating gears will always have to have the same number of teeth. Okay. And spacing of that teeth. So when you, or I'm sorry, not the number of teeth, just the spacing. So if you have something that's spaced differently, it won't match right. But if you have the right same spacing going on, then you can have two gears mated. Okay. Now, idler gear is going to be the gear in the middle. So if we have just two gears, like the top picture, we have a driver and a driven. Okay. An input and an output. Down below that, you see that the red gear is now just an idler gear. And why would you have an idler gear? Well, an idler gear is helpful because it helps change the direction. So if I have just two gears, if one's going clockwise, the other one has to be counterclockwise. But if we stick another gear in the middle of it, then the driver gear and the final output driven gear can be both going the same direction. Okay, so idler gears will be used most of the times to change direction of something. All right. And again, you look, we have a fancy word there, diametric pitch, but that was just what we were talking about with spacing. And again, gears have to have the same spacing or diametric pitch in order to be working together and connected. All right. Now, you will notice that anytime we have two gears and they're mated properly, if one gear has a larger diameter, it's going to have a slower RPM, all right, a slower spin to it. And that's always going to be the case, okay? Because of just the number of teeth. If I move 5 teeth with a smaller gear and 5 teeth with a bigger gear, the bigger gear won't move as much because it has many more gears to go, or many more teeth, okay? All right. Now notice that you can have, notice how we have the blue and the yellow gear and they're stuck together. Okay. In this case, they're not mated, right? They're stuck. And in this case, they would have the same RPM because they're sharing an axle. All right. So thinking about gears, there are 4 things that you can understand or read off of a gear. The number of teeth, okay? The diameter, which is, diameter from circle. And there's an example of where we want that diameter to be measured. All right. Angular velocity, which is really just RPMs. Okay. So in this class, RPMs and angular velocity are the same thing. How fast does it spin? And again, it doesn't matter how wide it is, but whatever it's spinning at, how many RPMs it is, that's going to be angular speed. And then finally, torque. And again, torque is important. Torque will cause something to rotate. The greater the torque, you've heard about torque maybe in commercials about a truck, where this truck has so much more torque than that. And it's just talking about how much it can rotate those tires pulling a heavy load. So there we go. Those are our 4 things we need to keep track of. Number of teeth, diameter, angular velocity, and torque. Okay. Reading off what we got there, we can count the teeth. So the blue, it gives us our teeth of 12. You could just count them. Okay. In our class, when we are in class and we have the gears from, say, Vex, they will have specific sizes where you can look it up and see how many teeth there are. With something like this, with a picture, you would just count them. All right. So you could count how many teeth. We give you RPMs. You can measure diameter. It gives you the diameter of both the 4 inches and the 2 inches. And then the torque is something that would be given to you as well, or we would calculate it and solve for it. Okay, so let's give it a shot. We see 2 gears. One is spinning at 20 RPM. One is spinning at 40 RPM. All right. The 20 RPM has 4 inches diameter, and the other one has 2 inches diameter. Okay. We also know that there are 12 teeth in the blue, okay, and 6 teeth in the red. So in going through gear ratio, it's going to be this formula. There's a lot of formulas. Okay. Gear ratio, which is a ratio. So it's gear ratio over 1, is going to be N for the number of teeth. So your output over your input. Okay. N output over N input. Diameter output over diameter input. Okay. Now, omega, again, with speed, notice how that's the only one different. So all of them are output over input except for the angular speed. The angular speed will be the opposite, input over output. And then finally, that T, okay, it's kind of like a lowercase t, except the top is cut off. All right. Torque. The torque will be output over input as well. Okay. So all 4 of those formulas will get you the gear ratio. It all depends on what you're given. Now we have all the information. So let's figure out what our gear ratio is with these. Okay. So how about teeth? I want you to do this. I want you to calculate all 4 of these. Why don't you pause it here and calculate it? So count by teeth, get the gear ratio, count by diameter, calculate by diameter, by angular speed, and by torque. We don't have the torque yet, but and by torque, and get those gear ratios. Pause it here and let's see what we get. Okay, we're back. Let's see what we got here. So calculating, we don't know the gear ratio yet. We're going to calculate that. Output over input, we have 12 divided by 6. We should know what that is. 4 inches divided by 2. Okay. We have our omega, 40 RPMs divided by 20 RPMs. Again, still a 2-to-1 ratio. Notice how all those units cancel out. Okay, because gear ratio won't have a unit to it. And then torque, that was from the previous page, 80 over 40. So again, those cancel out. And all of those get you the same gear ratio because they all should of 2 to 1. Okay, so your gear ratio is going to be 2 to 1 there. All right. Now, look at this gear train. We have 4 gears. What I would like you to do is we'll go step by step. I want you to calculate the gear ratio for each ones that I ask. Okay, so what's a gear ratio of A to B? Pause it here. All right, there we go. So we have gear ratio, output over input should be 12 over 20, 0.6. Okay, B to C, what you get there? Calculate it. Okay, B to C, 5 over 12. All right, so the gear ratio from B to C is going to be 5 over 12 or 0.42. What about C to D? Go ahead and pause and calculate that. All right, did you get 20 over 5 or 4? Okay, so there we go. So that's how you practice the gear ratios of one to the next to the next. But let's look about the whole gear ratio. The whole gear ratio, just like when we learned with compound machines. With compound machines, you take the simple machine mechanical advantage of each one and multiply them all together. It's the same thing with gear ratio. So to get the gear ratio of all of these, we can calculate. So I want you to do this. Calculate the total gear ratio. You are given 0.6, 0.42, and 4, okay, as our gear ratios. So if you multiply them together, what do you get? I want you to pause it here and do the calculation. Okay, so let's see. We got 0.6 times 0.42 times 4, and we get our gear ratio of 1 to 1. Does anyone see where maybe there's a shortcut? Well, let's see here. What if I just did my output to my input, or my A to D? So what if I just did A to D as my gear ratio? Well, if I did that, my output over my input, that's 20 over 20. I still get a gear ratio of 1. Okay, so with any machine like this, and I'm not talking about 2 gears that share an axle because that's different. Okay, if 2 gears share an axle and then connect along to something else, those you can't follow this rule. But if you have a gear train like this, that they're all just connected by teeth along, you can go straight from the gear ratio of the first one to the last, and you'll get the same answer. Okay. All right. So what if gear D had 40 teeth? What would that gear ratio be for the whole thing? It would still be 2 to 1. Okay. So you'd still get 2 to 1, whether you do A to D or you do A to B, B to C, C to D. All right. See, both ways it works. Now, gear ratios and mechanical advantage are similar but different. We're talking apples and oranges here. So when we do calculations, if we have something that has both a gear and a simple machine, or compound gears and compound machines, you have to keep those two values separate. You can't just multiply them together. All right. You can multiply everything that has gears and get a total gear ratio. You can multiply everything that's a simple machine and get mechanical advantage and get an overall mechanical advantage, but you have to keep them separate. Okay. So the formula is going to be the same. If it was mechanical advantage, you'd multiply out all the mechanical advantages to get the compound mechanical advantage. Gear ratio, the same deal. Okay. And it just some reminders of some things right there I'll let you look at. All right. So how about this? We have a compound machine with a gear ratio. So you need to calculate the compound machine mechanical advantage as well as its gear ratio. So I want you to pause it here, and you should have a mechanical advantage overall from both, okay, and gear ratio. Pause it here, do the calculation, unpause me when you got an answer. Okay, let's see what we got here. So let's go step by step. First up, we have a lever. We have a wheel and axle. Okay, so if it's hard to see, we have an effort here and a resistance, which would be where the the other part of that arm is connected to the gear. Okay, so it says the diameter, or I'm sorry, the radius of the gear is 1.5 inches. So that would be our first resistance distance, where our effort distance is on the end of the 4 inches. Okay, so you'd have to do the IMA of that. Then you have your gear ratio of this first gear to the second gear. Okay, remember output over input. Okay, and we're gonna have to calculate that. Then you'll have another simple machine of the radius of 0.6 inches here. Okay, that is now our effort, and our resistance distance would be the radius of 4 inches on the next arm. Okay, so let's go through and see about the calculation. So first we have 4 inches to 1.5 inches. So we have the IMA is going to be DE over DR, which is going to be 4 divided by 1.5. Okay, we get 2.67. All right, now our gear ratio, output over input. We have 24 tooth over 60 tooth. N out over N in. So we have 24 divided by 60. We get 0.4, and that's our gear ratio of our machine. All right. Finally, you have your last one where DE over DR is going to be our effort is only the 0.6 because that's where we're applying the force. Okay. You could also think of this as a third class lever. All right. And our resistance force is going to be the 4 inches. Okay. So we have 0.6 over 4. So there's our second mechanical advantage. Now, to do the whole calculation of everything, we have to multiply our mechanical advantages together. All right, so our mechanical advantages will be the first one times the second one, okay, and we get 0.4. Our gear ratio is just going to be our gear ratio that we already calculated because that's the only one we have, and we get 0.4. Okay, all right, let's check out this compound gear. So we got animation, thanks to PLTW. Okay. So we got those driving together. The blue and the yellow are sharing the axle. Okay, so you would not do a gear ratio from the yellow to blue. You would, because they're actually just sharing the axle. Okay, they have the same RPMs, but they are not teeth connected. Okay, and then finally we got the red one connected to the blue. All right, so if I needed to calculate the gear ratio of this whole compound gear train, I would do the gear ratio of green to yellow, get that one, output over input, and my gear ratio of blue to red, okay, and then multiply those two together. Does that make sense? The common we cannot do, it would not be, we could not do a gear ratio of going directly from green to red because the yellow and the blue are not going through teeth. They are connected together, sharing the same axle. Okay, so you could not go just green to red on this one. All right. So I want you to do the calculation. Let's do the first one. Gear ratio of A to B. Go ahead and calculate that. You get 4 to 1. Okay. Output of the 40. That the T is for teeth, by the way. All right. Over 10 teeth. So you get 4 to 1. All right. Now, what about C to D? Our gear ratio of there. Output over input. Go ahead and calculate that. All right. Whoops. So I jumped ahead. But we have 50 over 20. So you get 2.5, the gear ratio of the second one. Finally, the total gear ratio will just be our 4 to 1 times our 2.5 to 1, or 4 times 2.5. And we get a gear ratio of 10 to 1 for the entire gear train. Okay. Now notice 10 to 1 is not the same as 5 to 1. So if we try to do red or green to red, we'd get a different answer. All right. Now, belts and pulley systems, they will follow the same thing. It's still going to be the same ideas and same formula. It's just that there's no teeth on this one. Okay. So a belt doesn't have teeth. All the other equations are the same. Diameter, output over input. Okay. Torque, output over input. Omega, which is velocity, RPMs, again, is the one that's flipped, input over output. So do that calculation now. Go ahead and get the diameter, output over input, and the RPM, output over input, and the torque. If you see it, we got 18 1/3 and 55. Pause it here and do your calculation. Okay, how do we do? 6 to 2 for diameters, 30 to 10, 55 to 18 1/3, and those all have to be the same answer, obviously, because it's the same. You still got the system. All right, now sprockets. It's fun to say. You really should say it my way. All right. One thing is, so we don't have teeth, or we do have teeth on sprockets compared to belts. So you do have that calculation again and everything else. It's the same exact formula as going back to our gears. Okay. So sprockets, you're still going to follow the same thing and you're going to follow along. With sprockets, notice with both of these, they're going the same direction. Okay. So if two sprockets are connected, they have the same direction. If you have something on the outside of it, then it would cause it to change the direction. Okay. So go ahead and do your calculations here. Pause it and do your calculations now. How do we do? Let's see. All right. Output, input. Here we go. Teeth, output over input. We have what? 22 over 11. Diameter, 3 over 1.5. Okay. RPMs, input over output, should be 60. Whoops, 90. Sorry, I misread it. Okay. 90 over 45. And finally, torque, 120 over 60. So all of them get you the same answer. Obviously, they have to. And why would you wouldn't calculate all of them. You'd calculate with whatever you were given and what you needed. So you would not have to calculate all four, using all four, just the ones you need. All right. A quick way to remind you of pulleys and sprockets, belts versus the chain. Okay. And to be honest, this is how you compare garage door openers. Okay. If anyone has a garage door opener, you have usually 3 different ways. You could have a pulley or a chain or a big long screw. Okay. All those will do the same thing. But when you talk about advantages, pulleys will be louder as opposed to a sprocket. Okay. Pulleys, you don't need to have any oil or any other kind of lubrication for it, where sprockets is a chain. Think about your bicycle chain. With a bicycle chain, you need to have every now and then you got to grease your bicycle chain. If you don't, hey, guess what? You should go grease your bicycle chain. But you'll have a better strength where a belt can stretch. Okay, chain is much stronger. One time I noticed I asked my mechanic, hey, do I need to change the timing belt in my car? And he said, no, you don't have a timing belt. And if you don't know about timing belts, they tell you like every 100,000 miles, you better change that timing belt, because if it snaps, there goes the engine. Well, turned out I didn't have a timing belt in my car. I had a chain. Okay, so I had a sprocket instead of a belt system or pulley system in the engine of my little Toyota. Okay, all right, so disadvantages, pulleys can slip, and you've heard it. You've heard a belt, the serpentine belt in your car when it's slipping. If you ever heard of that older car going by and you hear that whining, hissing noise, that's from a slipping belt. Okay, sprockets are a little bit more expensive, but can be noisier. All right, so there you go. There's some comparison for you. And there's the resources. Thanks so much for watching, and I'll talk to you later.